So in this video, we're going to go over an example of using the second derivative test to identify relative extrema or local extrema, local max, local min values. So it says find the relative extrema for the function x to the fourth minus 4x cubed. We could kind of graphically analyze this. We could say, look, I know I have a local minimum here, and the local minimum corresponds to a place where the derivative is equal to 0, which is what we expect. We expect local min and local max values to occur either where the derivative is 0 or undefined. And I actually have two places where on the function f of x, which is in purple, where the derivative is going to be equal to 0. And what we can see is one of them is going to correspond to a local minimum, and the other is going to correspond to neither a minimum or a maximum. If we were using the second derivative test, what we would want to identify is that at f double prime, here's the second derivative, f double prime of 3 is clearly greater than 0 because we're above the x-axis. So the second derivative is positive at the critical number 3. And that tells us that the graph, because the second derivative is positive, it tells us the graph is concave up. And if the graph is concave up or opening upwards, we expect a minimum. Whereas here, the second derivative is actually equal to 0 at the critical number x equal to 0. So the second derivative test is going to be non-applicable in this case, because we need to know whether the second derivative is positive or negative to identify whether the graph is concave up or down. So if we just step through the process of finding the local extrema for the graph of f of x equals x to the fourth minus 4x cubed without looking at the graph, the process we would step through would be to first find the critical numbers. What are the x values for which the derivative is either equal to 0 because we have horizontal tangent lines, or undefined because we have something like a sharp cusp on the graph. So take your function f of x, rewrite it, and then find its derivative, which is going to be 4x cubed minus 12x squared. And the derivative is a polynomial, so we know it's not going to be undefined because it has domain from negative infinity to infinity. But indeed, f prime might equal 0, so we need to determine when does 4x cubed minus 12x squared equals 0. And I want to notice that a 4x squared is a common factor to both terms, so I'm going to factor it out, leaving behind x minus 3. And now I have a product of two algebraic terms equaling 0, so I'm going to use the zero product property to break it into two pieces. Either 4x squared equals 0, or x minus 3 is equal to 0. So either x is equal to 3 or x is equal to 0 when we solve both of these. So our critical values are going to be 0 and 3, and those are going to correspond to points on the graph. So what points do those correspond to? Well, we have to plug 0 and 3 into the original function. So if we calculate f of 0, we get 0 to the fourth minus 4 times 0 cubed is just going to be 0. So we get the ordered pair 0, 0 on the graph. So here's the point. And then if we plug in x equal to 3 into the original function, we get 3 to the fourth power minus 4 times 3 to the fourth power, and I wrote a 3. We get 3 to the fourth power minus 4 times 3 to the third power. So I've got a 3 cubed times 3 minus 4. So it's going to be 3 cubed times negative 1. And 3 cubed is 27. 27 times negative 1 is negative 27. So we have input 3, output negative 27, showing up as a point on the graph. And then the question is, do either of these 2 points correspond to relative extrema, local minimum values or local maximum values? And what we need to do is find the sign of the second derivative at the critical number. So to do that, I'm going to find the second derivative. So f double prime of x equals 12x squared from here minus 24x. And then if we plug in 0, we get f double prime evaluated at 0 equals 12 times 0 squared minus 24 times 0 is going to evaluate to 0. And that's the tan graph here intersecting 0 there. So the second derivative is 0. And that tells us that the test fails. The second derivative test is inconclusive. So the sign of f prime of x, it wasn't positive or negative, it was 0. So the test fails. The second derivative test fails. And to determine whether we had a local min or max there, we would need to use the first derivative test from the last homework assignment. I'm not going to do that, but if we talk through the first derivative test, we can see what would happen. So the first derivative test would say find the sign of the first derivative to the left of the critical number and find the sign of the derivative to the right of the critical number. And what I want to notice is if I find the slope of a tangent line to the left and to the right of that critical number, here the tangent line is negative, here the tangent line is negative. And the first derivative test says that if you don't have a change in the sign of the first derivative or the slope of the tangent line, if it stays negative and negative, then you have neither a local minimum nor a local maximum. So the first derivative test, were we to apply it, would identify that this point is neither a maximum nor a minimum value. And then we play the same song and dance with the other critical number. We plug 3 into the second derivative. So f double prime of 3 equals, here's my second derivative, so it's going to be 12 times 3 squared minus 24 times 3, and you just crunch this out. So this is 3 squared is 9, so we're going to get 90 plus 9 times 2 is 18 minus, and this is going to be minus 60 minus 12. So we're going to get 30 plus 6 is 36, and the key is that the second derivative is positive or greater than 0. And because the second derivative is greater than 0, that tells us that the graph right here when x is equal to 3 is concave up. And we know if something's concave up, we're going to have a minimum value. So the sign is positive, so we have a local minimum because the graph's concave up. Remember, if the graph is concave down, then the second derivative would need to be negative, and you would have a maximum value.